Let's continue in 7.6 and look at derivatives of inverse trig functions. Let's recall theorem 1 that says if f is 1 to 1, differentiable, and g is f inverse, and f prime of g of x is non-zero, then g, which is, right, f inverse, is differentiable, and d dx of f inverse is equal to g prime. This is just notation, right? But that's equal to 1 over f prime of g of x, or 1 over f prime of f inverse. So we're going to use this to define the derivative of sine inverse. So let g of x be arc sine with the defined domain restrictions. Then we say f of x is equal to sine x because f inverse is arc sine, right? And by the theorem above, g equals f inverse. So we have that g prime, but this is directly from the theorem, is equal to 1 over f prime of g of x. So now substitute in what we know. So what is, all right, so we have f prime of x is equal to what? So, so here's f of x. F prime is cosine x. So f prime is cosine x. So then we can say that g prime, so g prime of x would then be 1 over f prime of g of x. So that would be cosine of sine inverse of x. So we have cosine and sine. What we can do is convert sine or cosine into the other function so that we can actually take the inverse. So this is what we can do. We can rewrite cosine as a sine. So use the Pythagorean identity that's cosine squared theta plus sine squared theta is equal to 1. So we can then we're going to use cosine theta is equal to, we're going to use just the positive square root of 1 minus sine squared theta. That we're going to assume is greater than or equal to 0. And now we will substitute for cosine. So this will then be written like this. And so we have what we're substituting for is, here's your theta, here's your theta. So that's what, where'd it go? We will substitute sine inverse with. So you have g prime of x equal to 1 over the square root of 1 minus, and then we'll put in bracket, sine of sine inverse of x squared. And now we have that they're inverse functions. So the inverse sine of sine inverse is just x. So that equals 1 over square root of 1 minus x squared. So all I'm really doing is using this definition to substitute in the proper values. But I'm going to change cosine into this form. And so we get this, this becomes a root of what's inside. So that's what's inside. So here's the root, and then it's going to be, excuse me, squared of what's inside. And so that allows us to change this into sine of sine inverse, which is just x, with all the proper domain restrictions. Therefore, so we can just write what the derivative is. So therefore, dx of sine inverse of x is equal to that, is equal to 1 over square root of 1 minus x squared. So you want to be able to recognize this derivative. So when you see a root and a 1 minus something squared with a negative, so it's a value here minus something, that's a sine inverse situation. So what if you had like a chain rule situation? So you can look at it like this. Let's look at this example. So find z prime if z is equal to sine inverse of e to the 3x. Oops. So now you have sine inverse of something, right? And this is, so all you're really doing is applying this, and then you do the chain rule. So we say z prime is equal to 1 over, and that'll be the square root of 1 minus, and then it's e to the 3x squared, and then chain rule. So it's times, and I'll write it this time, ddx of e to the 3x. And that itself will need a chain rule, right? Because the derivative of that is itself times what's up top, which is just 3. Now, we won't write that twice. We'll just say this is equal to 3e to the 3x all over that root. So it's the square root of 1 minus e. And then we can write that now as 6x because you just multiply powers, right? That's pretty straightforward there. Okay. So you can define cosines similarly. So I'll just give you that one. So dx of cosine inverse of u. I probably should have done that for sine as well, but really for this one, if this is a u, I can just write it right here, like why not? So if that's u is a function of x, then it's just going to be a u down here, like that, and then it's times u prime, right? It's just chain rule. Okay. And so for cosine, you get something similar when it's derived, but you have a little restriction on this one. Normally they just kind of just start taking derivatives and don't really care about domain restrictions right off the bat. That's okay. We will just be aware that sometimes you got to do that. You got to be aware of all those domain restrictions. Handwriting's not great today. Let's see. Okay. So derivative of cosine inverse of u is negative 1 over root 1 minus u squared. and then of course times u prime. And this is provided you have the absolute value of u strictly less than 1. So that has to be true. Otherwise, this will be an imaginary number. So you have to have 1 minus, and then this product has to be less than 1. Back up here for sine is the same restriction. So yeah, you still have to have the same restriction. So absolute value of u less than 1. Otherwise, you have the same problem. Okay. And that's usually fine because what you're substituting into the functions are usually between -1 and 1. Okay, next one, let's just do tan inverse. Let's see, okay, so I derived tan inverse. So let's do this in the next page. All right, so let's find tan inverse. Okay, so our goal is to find d dx of tan inverse of x, or arctan, however you want. I interchange these back and forth. So let's let y equal tan inverse of x. Then tan y is equal to x. Okay, so that's just the definition of tangent. And then what we're going to do is differentiate implicitly on both sides. I'll just abbreviate everything. You can hear me say that. Differentiate implicitly on both sides. And so we start with tan y equal to x. And so let's now differentiate. That implies that d dx of tan y is equal to d dx of x. Okay, and that is equivalent because now I have the derivative, so now the next few steps are if and only ifs. And just to be clear on, hopefully clearer, is that this, when I'm saying implies and if and only if, that's a big difference. I'm saying this, if this is true, it implies the derivative is true, but going backwards is not always the case because you can lose a constant. So if I had a plus c in here, don't write this down, then they are not equivalent, right? So I'm being usually very careful of when I say if and only if or implies. Okay, let's move on. Enough of the logic for now. So that is true. So derivative of, what's the derivative of tangent? Look that up. And you're right, it's secant squared y. But then it's times y prime using implicit differentiation equal to 1. And so if we solve for y prime, that is if and only if, y prime is equal to 1 over secant squared of y. But we know what y is. Y is, well, it's tan inverse, so we got to do a little step here. So what we got to do is we'll say y is equal to 1 over 1 plus, oh, okay, I see what I used. Now I'm using another identity. All right. So this is an identity. It's the Pythagorean identity, just simplified. So we use the identity of secant. And so secant squared is 1 plus tan squared y. It was 1 plus tangent squared y. So this is an identity. If you're not, well, remember that, look that up. So use this identity. It's the Pythagorean identity. It's just dividing by cosine, actually. And so now what's y? Well, y is tan inverse, and then you get the inverse relationship here. And so this equals 1 over, and so it'll be 1 plus tangent of tan inverse of x, quantity squared. And so since they're inverses, this is of course just x. So that's 1 over 1 plus x squared. And we have it. Therefore, we've derived tan inverse. So d dx of tan inverse, and I'll just use a u because you just use chain rule again right there, is equal to 1 over 1 plus u squared. That's what you remember. And then times u prime if we have to apply the chain rule. No critical restrictions on u because it's being squared and you're adding, so we won't worry about that right now. Can't be -1, but that would be imaginary, right? So don't have to worry about that. All right, so going back and forth between these, so if you integrate this, then you get this. So integration of this is tan inverse. And then similarly, for sine, we have another integral formula right back here. So for sine, integrate both of those, you get, so integral of this is sine. So we have some integral formulas we will be using. There's more, but these are the ones I was going to just show you right now. So integral formulas. We have that the integral of 1 over square root of 1 minus x squared dx is sine inverse of x plus c, and the integral of 1 over x squared plus 1 dx is equal to tangent inverse of x plus c. So those are the main ones you need to know and memorize. And you also have cosine. We could throw cosine in there too. Where'd cosine go? So here's cosine. So this one's cosine. It's not as nice because you have the negative floating around here. So if you have like an opposite and integral, then you get cosine inverse. Okay, so these are the more standard ones. And well, but do you see that they're really the same? And it's really the same thing. So if you had this being negative, you could have cosine inverse. It's just shifting it. So these are the main ones we focus on. Okay, so next we will do some examples of integration, and that'll be it for this section.